Welcome to The Explainer. Today, we're diving into the high-stakes, ridiculously fast-paced world of industrial manufacturing and robotics. We're tackling a massive, incredibly expensive problem: motor failure. But to solve this giant industrial headache, we aren't building bigger machines. We're actually zooming all the way down to a microscopic solution. We're going to see how we can essentially read a machine's mind just by listening to its magnetic heartbeat.
Okay, let's dive right into this. Picture a modern smart manufacturing facility, or maybe a massive, complex robotic system. These places are literally powered by hundreds, maybe thousands, of critical electric motors running 24/7. Now imagine the sheer chaos and the financial hit when one of these vital motors just unexpectedly fails. The whole assembly line just grinds to a halt. It is an operational nightmare. That's exactly the problem we're unpacking today, and we're looking at an astonishing new way to actually predict these failures way before they ever happen.
So, here's our roadmap for today. We'll cover the motor maintenance problem, look at a microscopic magnetic solution, design the CMOS magnetometer, check out some real-world motor testing, and finally look at the future of smart maintenance.
Let's kick things off with Section 1, the motor maintenance problem, the industrial muscle.
This brings us to a concept that's absolutely crucial for the industry: condition-based maintenance, or CBM. The whole idea here is simple but incredibly powerful. Instead of just replacing parts on a blind, set schedule, you monitor the machine's actual real-time condition to predict exactly when maintenance is needed. It saves a ton of time and money. But there's a catch with how we do it right now. Traditional diagnostic methods, stuff like thermal imaging, ultrasound, or vibration analysis, well, they're what we call lagging indicators. Basically, by the time a sensor picks up excess heat or some terrible vibration, the physical damage to the motor, it's often already started. So let's compare those traditional sensors with a totally different approach: magnetic flux analysis. Now, while vibration and thermal sensors have been researched to death, magnetic flux analysis is actually surprisingly under-researched for motor fault detection. Think of it as a hidden sixth sense for machines. Because motors fundamentally run on electromagnetism, right? So any changes in the magnetic field give us this immediate, direct look into the electrical health of the motor, long before any physical shaking or overheating even begins.
Moving right along to Section 2, a microscopic magnetic solution, a microscopic innovation.
So, the real magic is in how this sensor is actually built. To make this work, researchers developed an incredibly sophisticated tool using the cutting-edge TSMC 180nm CMOS foundry process. They created these ultra-sensitive search coil magnetic sensors and integrated them right alongside a low-noise readout circuit. This whole microscopic package is so innovative for the health monitoring of critical motors in smart manufacturing and robotic systems that it actually secured a PCT patent in 2025. It's literally a massive leap forward for predictive maintenance.
Now here is the real aha moment. What's truly fascinating is the power requirement, or, well, the total lack of it. This micro-variable reluctance sensor, or micro-VRS, is 100% passive. It operates without any power source whatsoever. Zero. If you compare this to standard semiconductor-based magnetic field sensors, like those power-hungry Hall effect sensors, this is a total game changer. Complete passivity is basically the holy grail for IoT deployment, because you can stick these sensors anywhere without stressing about wiring up power or swapping out batteries.
All right, Section 3, designing the CMOS magnetometer from theory to reality.
And this brilliantly illustrates the gap being bridged between theory and reality. On the left, you've got the theoretical schematic of the low-noise instrumentation amplifier that processes the signal. And then, over on the right is the actual, tangible HKUST fabricated chip. It takes all that brilliant theory and condenses it down into a highly compact, totally manufacturable reality.
This tiny chip delivers some seriously surprising results. Initially designed using low-cost, 6-layer PCB technology, it achieved a record sensitivity of 6.2 picoteslas per root hertz for a uniformed 100 Hz magnetic field. Now, picotesla is a ridiculously small measurement. It basically means this device is hypersensitive to the absolute most minute magnetic changes. And that is exactly the kind of tiny fluctuation a motor makes right when a fault is just starting to develop.
Next up, Section 4, real-world motor testing, vacuum pump validation. Just take a look at this stark juxtaposition of scale. Here we have a heavy, industrial, 250-watt Edwards rotary vane vacuum pump. And placed right on its cover, that is our microscopic, passive CMOS search coil magnetometer. The goal here is simple:
Continuously monitor the magnetic flux of this heavy-duty motor while it's running, using a sensor that barely takes up any physical space at all.
To actually prove this sensor works, the researchers couldn't just wait around for a machine to break naturally. I mean, that could take years, right? Instead, they developed a really systematic methodology and sequentially induced specific faults. Step 1, mechanical faults, like intentionally causing bearing wear or a misalignment. Step 2, electrical faults, like short circuits. And Step 3, operational faults, like forcing overload conditions. By doing this, they could map out exactly how the magnetic field changes in response to each specific type of damage.
And the preliminary findings reveal something pretty remarkable. The researchers found that the passive PCB search coil magnetometer has successfully measured the magnetic flux and detected these faults without needing any extra signal amplification. Just really think about that for a second. No extra power, no extra boosting. Just a completely passive sensor successfully reading the subtle warning signs of a failing motor. It definitively proves its viability for long-term, low-power sensing systems.
And finally, Section 5, the future of smart maintenance, the AIoT era. When you've got a tiny, passive, highly sensitive sensor like this, the systemic benefits are massive. You can deploy dense networks of these things across a smart building for non-invasive, continuous monitoring. By driving true predictive maintenance, you prevent massive energy waste from inefficient, failing motors. But honestly, it goes way beyond just machines. These sensors are so sensitive to magnetic fields, they can actually detect the fields generated by human movement and electrical devices. That means you can use them for occupancy detection, automatically optimizing HVAC and lighting systems based on where people actually are in a building. That drastically reduces the carbon footprint of smart buildings.
As the research report concludes, this is a significant step forward in creating innovative solutions for building maintenance. We've seen how a microscopic advancement in 180-nanometer silicon architecture is directly solving massive, real-world industrial and environmental challenges. By simply listening better, we can make our factories, our robots, and our buildings far more resilient and efficient.
So, I'll leave you with this to ponder. If a completely unpowered, microscopic sensor can predict when a massive industrial machine is about to fail just by reading its invisible magnetic heartbeat, what other hidden data streams are flowing all around us, just waiting for the right sensor to uncover them? Thank you so much for joining me for this explainer, and keep staying curious about the invisible forces shaping our world.